Greetings everyone. Today we're going to take a look at describing graphs, which includes all of the key features and ways that we can describe a graph in order to visualize it and to understand the information. So I have a foldable for this to make it easier to take some notes. You still need your notebook as well because we're going to do one additional example in there. Don't forget, as always, to make a little left column or glue the foldable off to the side just so you have some room around it. Learning top targets that we're going to hit today, we're going to talk about local and absolute maximums and minimums. We're going to talk about where graphs are increasing and decreasing. We're going to talk about intercepts, which you're probably even more familiar with already. We're also going to talk about, is a graph continuous, how it's bounded, and if it's even, odd, or neither, which should sound familiar. All right, so here's your foldable. Make sure you fold along the blue lines and then cut along the red so you have those 4 flaps that you can open and check out the information. All right, let's take a look at the inside of our foldable. First, we want to go over intercepts in the top left. So the blank is the point where the graph crosses the x-axis. You're familiar with this. That is the x-intercept. So in this particular graph, we have 3 x-intercepts. You identify intercepts using their full coordinate name. So -30, 10, 50. The blank is the point where the graph crosses the y-axis. It's the opposite. It's going to be the y-intercept. And because this is a function, we should only have one y-intercept in order to pass the vertical line test. And that y-intercept is +2. All right, so let's take a look at increasing and decreasing. A function is blank over an interval if the y value increases as the x value increases. If everything's increasing, it's increasing, okay? So consider this, a couple little tips when you're dealing with increasing and decreasing. It's probably going to be the toughest part of this process. If we're talking about increasing, we always read the graph left to right, okay? Meaning if I start here at the left and I start drawing on the graph, I'm going up. I'm increasing from the left side going up, okay? So increasing, and then I'm changing direction. I'm not increasing anymore, but then I'm increasing again from this direction on, okay? So now to describe those increasing places, like how do I say where it is, where does it occur, okay? We use what's called interval notation. And for that, for the interval, we always use the x values, okay? So we need to use one type of value, and if we're reading left to right, that's the x-axis, so we use x values. So my first interval that we highlighted occurs from -infinity, because I can't draw how far left that graph is. So it's from -infinity all the way to the x value of -1. Okay, so that's what I'm talking about here. -infinity all the way to -1, I'm increasing. And then I pick back up at 3, and from 3 to where? Well, it goes forever in that direction, so to +infinity. So forever left is -infinity, forever right is +infinity. And then we're looking at where does it change direction. So let's look at the opposite. A function is decreasing over an interval if the y value decreases as the x value increases. So it just makes sense more visually. I'm decreasing as I read left to right here on this blue segment, okay? So again, I need to describe that somehow. I'm decreasing from the x value of -1 to the x value of 3. Okay, we're going to stick to parentheses in these intervals because we can't include them. Like I'm not increasing at the point, I'm increasing up to the point. So we're going to stick to parentheses. Also notice that if I piece all my intervals together, I have the whole graph, right? It's continuous. So -infinity to -1, -1 to 3, 3 to infinity. They sort of all piece together, right? So increasing, decreasing, I'm not gonna lie, that's gonna be probably the toughest piece in my experience as far as remembering to use the x values. All right, let's take a look at maximums and minimums. The maximum is the y value of the highest point in a particular region of the graph. In this case, the highest point, keyword point, is going to be at -1, 4. Sometimes we'll have more than one maximum. Think of it as the tops of curves or the tops of V's, or where it changes direction. Therefore, the opposite has to be minimum. The minimum is going to be the bottom, the lowest point on a graph. Key thing again, it's a point. The lowest point on this graph is 3, -4. So we don't say infinities are the lowest because those aren't points. So we care specifically about points. I need to stress that. All right, when we talk about the bottom right there, the y value is 0 where? Well, we talked about it a little bit already, but there's some synonyms you need to be familiar with. So we're going to talk about zeros, roots, solutions, and intercepts. So we talked about x-intercepts already, okay? But know that roots, solutions, and zeros are synonyms for that. So in this case, I would say my solutions are x equals -3, 1, and 5. So when we're listing them as solutions, we can just say the x value. When we're listing them as intercepts, we typically use the points. All right, a couple other things we need to add into our notes. Feel free to abbreviate this as necessary. Continuity. So this is specific to our class. We're going to talk about continuity. And continuous means, graphically speaking, a function's continuous at a point if the graph does not come apart at that point. So in this case, the graph is continuous always. It doesn't stop. There's no breaks in the graph. And you might be thinking, when is there breaks? We'll take a look at some examples here in a little bit. So in this case, this graph is continuous from -infinity all the way to infinity, or we could say all reals. It's forever continuous, all right? It doesn't stop, there's no breaks. So continuity has meaning. Other features that we're going to be discussing specifically in this class are boundedness. All right, my suggestion would be to pause this video, write these notes down. That way you can listen to the descriptions, try to separate the writing and the listening. So first of all, boundedness. If a maximum or minimum exists, we have what's called an upper and a lower bound. Okay, so bounded below, a function f, for example, is bounded below if there's some number b that's less than or equal to every number in the range of f. The number b is called the lower bound of that function. Okay, so let's look at the opposite, bounded above. A function f is bounded above if there is some number b that's greater than or equal to every number in the range of f. Any such number b is called the upper bound of f, of the function. Okay? A bounded function, meaning bounded above and below. Okay, so let me sort of summarize this and give a quick little sketch. Bounded below versus bounded above versus bounded above and below. Bounded above and below, and we're not going to encounter this very often in our class, but when we talk about sine and cosine functions, those are bounded above and below because we sort of have this upper bound limit that it never crosses, and we have a lower bound that it never crosses. So it's bounded, it's restricted within those boundaries. That might help you can make that connection. Bounded above, it's bounded above if there's some number b that's greater than or equal to every number or range of f. So what that's going to look like is if there's a boundary above the graph. So that might look something like a curved graph like this. Okay, this is going to be bounded above because there's a boundary here that it's not going to cross. All right, which means the opposite, bounded below. That might mean, let's do an absolute value graph here. In this case, I have bounded below because there's a boundary below that it does not cross. Okay, so boundedness, such a weird word to say. Think of it like a boundary, what you're familiar with already. Okay, so a visual look. Here's some more examples just to quickly, don't need to jot these down. In this case, an exponential function is bounded below because we've got that boundary below it. This is a quadratic function. It's bounded above. It's an upper bound because it doesn't cross that boundary. Sometimes you can have not bounded. This one goes forever up and forever down, so there is no boundaries at all. And then again, that example I provided you of a sine function, which is bounded above and below. All right, so a few other key features. I know this is a lot of information, bear with me. When we put it all together, it'll make more sense. When we talk about maximums and minimums, there's sort of two different types. So first, let's talk about maximums here. Okay, a local or relative maximum is a high point on a certain interval of the graph. A graph can have more than one local maximum. Oops, sorry, that's a typo. That should say maximum right there. Okay, meaning it's every high point. If you wanted to abbreviate this, a local or relative maximum is every high point. So you can have more than one. It's every peak of a curve, every top of a mountain, however generically you want to describe that. Okay. Key thing though, they're points. Okay, so we write them as points. An absolute maximum. Okay, very specific. Absolute is this key word. Is the highest point on the whole graph. Okay. Now, absolute maximum can be a point, but if a graph is continuous above, if it goes to infinity, we say it is infinity. Okay. So if it has an upper bound, then it's going to be the highest point. If it does not have an upper bound and it goes forever up, we say it is infinity. Okay? So what's the absolute highest point that graph goes? The name, just think of it very literal, absolute. Therefore, the opposite is true when we talk about minimums. Okay, let's abbreviate this. A local or relative minimum is every low point that's included because you can have more than one. So every bottom of the valley, bottom of the curve, bottom point, okay, is considered a local or relative minimum. But more specifically now, okay, an absolute minimum is the lowest point possible. Meaning if it goes forever down, if there's no lower bounds, we say it's negative infinity. Okay, so what's the lowest or the absolute lowest point we have? The last key thing we're going to talk about is even, odd, or neither. And here's the thing, guys, you've already done this at the beginning of the year, okay? It's even if it's symmetrical around the y-axis, right? So that looks like maybe a parabola. Maybe we have some type of absolute value graph that's reflected in the y-axis, okay? Odd means it's symmetric about the origin, all right? Those graphs look more like cubic functions, meaning if it's a perfect 180-degree rotation around the origin. So if I turn and turn, or that's where that idea of double flip came into play. It's a double flip around the x and the y-axis, then it is odd, okay? Neither. Sometimes you can have no symmetry, so that's probably going to be more often than not, to be honest. You might have something that's symmetrical, right? A parabola is symmetrical, but it's not around the axis. So this is not even or odd. Neither is an option. Okay, so let's take a look at this example. You do not have to write this down. So let's just follow along, make sure we understand all these concepts we just went over. First thing I'm going to talk about is x-intercepts, okay, where we cross the x-axis. If you have to make an assumption or a round, please do so. So I see an x-intercept at -4, 0. I see an x-intercept at -3, 0. I see one at maybe 0.5, 0, and at 3, 0. Y-intercepts, this is a function, so it looks like I have one y-intercept at 0, -2. This is not symmetrical around the origin or the x-axis, so in this case I'm going to say neither. Is this continuous? Does it go forever, and are there any breaks in the graph? So yes, it's continuous. It doesn't stop, it's just a continuous curvy function. Boundedness, are there any boundaries? Okay, yes, there is boundedness, and we would call upper bound. There's an upper bound, meaning an upper boundary, okay? Increasing intervals. So if I read left to right, I'm going to trace my graph. So as I'm going, what am I doing here? I'm increasing. So I'm increasing up to here, and then I stop, all right? Then I'm not increasing, and then from here, as I trace. So use your finger, use colors, whatever you need to do. I'm increasing here. And that's it. That's the only time I'm increasing. So my increasing intervals, I'm starting at the forever left option, and I'm increasing all the way to what x value? If I had to guess, let's say -3.5, okay? And then I'm also increasing, it looks like here would be maybe -1.5, and I'm increasing all the way to the x value of 2. All right, remember, left to right, x values is what I'm looking for. Decreasing, where am I decreasing? Well, let's see. From here, as I read left to right and trace the graph, I'm going down, so I'm decreasing. And then from here on, I am decreasing. So again, I'm decreasing from that same x value of -3.5 all the way to the x value of -1.5. Notice how those values match up, you guys. That matters. I need these to be associated with each other. Okay? Then I'm also decreasing from that x value of 2 to forever. So positive infinity. There's that 2 and that 2. They're all connected. And because it's continuous, those intervals all piece together like a puzzle. All right, let's talk about maximums and minimums and identify if they're absolute or local. So first of all, let's talk about the tops and bottoms of curves. I'm going to start with maximums. I've got a top here and a top here. So as a point, I would say that that's -3.5, 1. And I have a maximum, it looks like, at 2, 5. Okay. If I take a look, 2,5 is the highest my graph goes. So this is an absolute max. That's the absolute highest this graph goes. And then the other one's just going to be relative. It's a top, but it's not the absolute. So it's a relative maximum. Take a look at minimums. Okay. Minimums, I've got a bottom here. So that looks like it was at -1.5, -5.5, a little bit of rounding. So is that the shortest, or excuse me, the lowest that graph goes? No, it's not. So that's actually a relative minimum because it's not the lowest. And then also it goes forever down. So my absolute minimum is -infinity because it goes forever down. Okay, domain and range. All right, let's review that. Domain and range talks about domains the x values, how far left to right, ranges y values, how far low to high. So we use x values left to right, and we use y values low to high. Does that make sense if I abbreviate it that way? So this graph goes forever left, and this graph goes forever right. We're going to use interval notation to describe that. So even though it's going down, it's still going forever left and forever right. For range, how low does it go? This graph goes forever low, so negative infinity, but it stops. It has boundedness. So the highest this graph goes is to 5. And I'm going to use a bracket. That 5 is included in the graph. It's included in how high that graph goes. So we're going to use a bracket. Okay? All right, let's take a look at another example. I know this is a long one, guys. Hang in there. If you need to take a break, pause it, go walk around a little bit and come back. This one, I do want you to try to do a quick sketch. I made it kind of easy points so that it'd be easy to draw. So please pause the video, graph it, ask the questions, and then come back and press play again. All right, first of all, let's talk about x-intercepts. Where do I cross the x-axis? 0, 0, and 3, 0. All right, let's talk about y-intercepts. Where does it cross the y-axis? Hey, it's still crossing at 0, 0. If it goes through the origin, I should see that in both intercepts. Okay, even, odd, or neither. Definitely neither. There's no symmetry even to this graph. Continuous. All right, here's where a graph is not continuous. Okay, you'll notice there's a break here. When I look at that break, it stops and then restarts. So this is not a continuous graph. Okay, so, oh, excuse me, I didn't mean to erase that. I meant to erase this. So this is not continuous. Boundedness. Is there any boundaries that you see? Yeah, we're not going beyond this. So we have an upper bound, an upper boundary. Okay. Increasing intervals. When am I increasing? So I'm going to read left to right. So as I trace with my finger, I'm increasing to here. And then I'm increasing to here. And then I'm increasing to here. And that's the only time I'm going up, okay? So increasing intervals. I'm increasing from negative infinity to negative 2, parentheses. I'm increasing from negative 1 to 1. And then I'm increasing from 1 to 2. Remember, these are all x values that I'm using here, okay? Notice I have that break at the 1 because I have a break at 1. Decreasing, when am I going down? From here on, I am going down, down, down. So for x values from 2 to infinity, I am decreasing on this graph. Okay, now you'll notice there's a little patch there that we didn't use from negative 2 to negative 1. That's not increasing or decreasing. That's steady, okay? So in that case, it's constant, and I'm not going to ask you that question, but just make note of what that is. Maximums and minimums. Identify if they're absolute or local. So let's look at tops of curves and bottoms. Well, I definitely have a top right up here, okay? So at 2, 3, and it's also my upper bound, so that's going to be an absolute maximum, okay? If I look at my absolute minimum, this graph is going forever down. So in that case, negative infinity is going to be my absolute minimum, okay? Now, if we take a look, we have other points where we sort of change direction here. We've got these 2 points, and then we have where the break is, okay? We're going to talk about those another day, but just keep in mind those have meaning as well. Domain. How far left to how far right does this graph go? Now, this is going to be very specific, okay? I'm going forever left. Remember, this is x values left to right. I'm going forever left, okay? But if I have a break here at negative 2, so at negative 2 I stop, okay? I pick back up at negative 2 because it's an open circle. And I'm going forever right. Now take a look at that 1 value. There's a solid dot and an open dot. So 1 is included on this graph, okay? Then I'm continuing here, a solid dot here, and I'm going forever right. So from negative 2, I'm actually continuing to infinity. All right, every point, every x value has a point or a value, okay? Range, how low to how high. I'm going forever low. We already talked about that. So again, y values, low to high. How high am I going? Well, if I look, I have a point at every y value all the way up to 3. There are some breaks, but in these breaks, I have a point somewhere, okay? So that's what matters, is that I have at least one point somewhere in that range. All right, so let's take a look. I know that was a long one. Thanks for hanging in there. It's a lot of information to take in. The thing that I really want you to work on is going to be those increasing and decreasing. Those are going to be the tough ones. Okay, so watch out for using the x values for increasing and decreasing. And then also, anytime there's breaks, we're going to keep working on those. Those are tough ones when there's breaks in the graphs. All right. Make sure you check Google Classroom, see if there's anything else you need to do. And let me know if you have any questions or if you would like some more practice on some of these. I can easily print off some graphs and we can answer the same questions. All right. Until next time, have a good one.